Okay, so next we have something called the handshaking lemma. So this is sort of when we're getting into proofs. So the handshaking lemma is basically a statement or a mathematical statement that the sum of the vertex degrees is always equal to double the number of edges in the graph. So if the sum of the degrees in a graph is 10, then the number of edges in the graph will be double that. It will be half of that. So 5. So we will have 5 edges if the sum of the degrees is 10. So in this graph, we will have the degree of A is 6, the degree of B is 5, and then 4, 2, and 1. And if we add them up together, we will get 11 plus 4, 15, plus 3, 18. So therefore, we will expect 9 edges on the graph, according to the handshaking lemma. And indeed, that is the case. So we have 1, 2, 3, 4, 5, 6, 7. Sorry, how do I count this? 1, 2, 3, 4, 5, 6, 7, 8, 9. As you can see. Just another note that I want to make, a side note, is a loop actually contributes to 2 degrees. So although it's the same edge recurring on the same vertex, so let's say if we're looking at it from this side, this edge just looping back to the same vertex, it actually contributes to 2 degrees because we're looking at how many connections are going out of the vertex or into the vertex, depending on how you want to see it. So that is why the degree of C is 4, but the degree of E, for example, is still 1 because we don't have any loops. Okay, so now we have planar graphs. So planar graphs are a type of isomorphic graph that can be drawn without any edges overlap. So basically a graph which we can redraw as an isomorphic graph where none of the edges are overlapping. So remember, from a few slides back, an isomorphic graph is a graph that has the same connections but looks a bit different. And a planar graph is basically a graph where an isomorphic graph or a similar graph exists where the edges do not overlap. So for example, this one, if we take this edge out and draw it like this, such as down over here, and also this one over here and draw it like this, we get an isomorphic graph. It's called an isomorphic graph because it's the exact same graph, just different look to it. The connections are the exact same, the degrees are the exact same. And here we have no edges overlapping, so we call this a planar graph. So a lot of the time you'll get questions like, is this a planar graph? And you'll get this graph over here. So right now, currently you can't tell, so you have to draw the isomorphic graph. And if you can't find any way of drawing the graph without having the edges overlap, then it is not a planar graph. So it's a little bit of trial and error when it comes to these sort of questions. Oops. Okay, so then we have Euler's formula. So Euler's formula is basically, again, a proof. A proof that something is a... sorry, what was I going to say? Oh yeah, so it's a proof to show that something is planar, or a graph is planar. And the way that it basically works is we have a planar graph, and the Euler's formula is that the number of vertices plus the number of faces minus the number of edges should be equal to 2 in order for a graph to be a planar graph. And we can only work out the number of vertices, faces, and edges if it's in the planar form. So for example, for this one, where the edges are overlapping, we can't work out the number of faces. And just before I get started on what a face is, it's just basically, before I get started on the Euler's formula, a face is basically the enclosed regions within the graph. So for example, this is a face over here between A, B, and D. This is a face between A, C, D, B. this is a face between EDC, and this is actually also a face. So we consider the outside region as a face as well. But if you look at this graph, which is not planar, oh well, technically it is planar, but just hasn't been drawn in the planar form, we will technically count it as 1, 2, 3, 4, 5, 6, and 7 faces. So that's where we make our mistakes. It's really important to convert the graph to planar form before proving using the Euler's formula that it is planar. And basically all we need to do is we need to sub in the information into the formula. So the number of vertices, so 1, 2, 3, 4, 5, plus the number of faces, so we just have 1, and remember the outside region is also a face. So 1, 2, minus the number of edges, 1, 2, 3, 4, and 5, is equal to 2, as stated. So therefore, this graph would actually be considered as a planar graph.